Okay, so this seminar is about a method for interpreting drill hole data, and what differentiates it from many of the other approaches out there is it's a multiscale approach. And so I'm going to go through the reason why we developed this method and how it helps you interpret your drill hole data. Once I've gone through the background details of how it works, I'm going to pass you over first to Margot and then to Jessica, and they're going to give you some case studies, so examples where we've actually used this in projects. Okay, as you know, manual core logging can be problematic because it gives very inconsistent results. So core logging is done by hand. A geologist makes observations and they write it down on a piece of paper or they put it into some sort of tablet. And the problem is that if you've got more than one geologist logging, that each geologist might log slightly differently because their experience in geology is different. And even if you've got one person logging over a long period of time, they may change over time because they develop more experience and more understanding of the rocks. And I'll give you an example here. These two plots here from the Sunrise Dam. They're just from one ore body, the GQ North ore body, and that pie chart shows the number, the proportion of meters logged by each geologist. And you can see there was a huge number of geologists logging it. And many of those geologists only logged a very small amount. And so this was very difficult. When they came to build the geology model, it was really hard to build it because every geologist has slightly different labeling techniques. And the second plot there, you can see a line graph. That's how many meters, well, proportion of meters that each geologist categorized by foliation intensity. And you can see the problems here that, you know, it was really important to get the foliation intensity right because this was a shear hosted gold deposit. And you can see some geologists wanted to have no F1 category and some geologists wanted most of their data to fall into F1. Now this could be real, it could be that some were mostly logging shear zones and some weren't, but when we actually came to build the geology model, we found that you couldn't correlate from one drill hole to the next where they used the foliation intensity. So why is this important? Well, there's a number of reasons, and the one that I was really focused on is building 3D geology models. And if you can't confidently correlate between your drill holes, then you can't build a geology model. And so here's an example I've just pulled off the web, and you can see it's a very beautiful example that everything's very consistently logged in these drill holes, and they were able to correlate very easily between the drill holes and build a geology model that had some sort of geological knowledge embedded in it. So if we look at this model, we can see that it's made up of geological layers, we can see faults, we can see folds, we can see cross-cutting patterns, we can see patterns where things are coherently stacked on top of each other. And so if you have geological information, you can build this kind of model. Now, there's basically two things you need to build a model from the drill holes. And one is geological information. So, for example, if something is labeled, say, as a floodplain, if something is labeled as a floodplain basalt, this is you're going to model this very differently to something is labeled as, say, a channel conglomerate. Now, we know channel conglomerates don't extend very far laterally. And so, you know, if we saw a channel conglomerate in one drill hole and then another drill hole maybe 100 meters away, we saw one again, we may not correlate them because we say, well, unless it's a very big system, they're probably not the same channel. Whereas if it was, say, a floodplain basalt, a floodplain mudstone or some sort of flood basalt, then you would know that you can, from your geological knowledge, that you can correlate over these large areas. So it's really important to have that geology label, which tells you how to connect things in your geology model. The other thing that you need to build a geology model in all this 3D modeling software is surfaces. Okay, and these surfaces are boundaries. So we look at the boundaries, and the first stage when you build a geology model is to correlate the boundaries from drill hole to drill hole. So there's two important aspects. If we want to build a good geology model, we need all the boundaries that we can correlate, and we also need to know some information about what the rock type is. Now, because we're having this problem with correlating from drill hole to drill hole, from doing manual geology logging, companies are now saying, okay, well, let's collect numerical data, because if we know that if we properly calibrate our machinery, then we know that if we got the number 5 in this one drill hole and the number 5 in another drill hole, that is actually the same number, and we can be confident about connecting across. And now when you upload that sort of information into a 3D modeling program, what you can do is you can build 3D isosurfaces. So that top diagram there on the right is a typical isosurface model you might get from using some sort of numerical analysis of features in your rock. It might be geochemistry, it might be physical process, it might be physical features. But the problem with these isosurfaces is the isosurface is just a representation of the distribution of data in 3D space. It's not a geological boundary, okay? They're not igneous contacts, they're not sedimentary contacts. They have no geological meaning to them. They're just a visualization technique. So you're missing that really important information for building a 3D geology model. And the other thing that you're missing is this is univariate. You can only put one variable in at a time. So if you're doing, for example, multi-element portable XRF, you can only model one element at a time or one variable at a time. And this is very limiting, and it doesn't allow you to put a lot of geological meaning onto that data. So we could manually interpret the numerical data, and that's what people started doing, but of course that's very, very slow. So people have started now looking at automated interpretation. How do we integrate all this numerical data together and provide an automated interpretation? And there's cases where you would and wouldn't use an automated interpretation, but basically the times when it would really help you is, for example, if you have a very large data set, you simply don't have time to interpret it manually. You may have many drill holes, or you may have a very deep drill hole, or you may have very closely spaced data, and it's just going to take you way too long to do that manual interpretation. If you have lots of variables, you can find it very hard to combine them all together into a single interpretation. You know, how do you plot them out? How do you visualize it to be able to actually integrate them all and do a simultaneous interpretation of them? The other thing is, if you want to experiment with different interpretations, now traditionally if you're on a mine site and you're very pressed for time and you have to build a geology model, you'll only build one geology model because it might take you weeks to build it, so you really only have time within the production timeline to build just one geology model, and it doesn't give you a chance to experiment with different interpretations. If you were able to very quickly build multiple versions, testing out different ideas that you might have, you would have a much better idea of what the uncertainty of your final model was. Okay, and finally, the really important time is if you have a whole team of geologists logging and you're worried that your team is not logging consistently. That's when the automated methods are going to be really useful. Okay, so one of the solutions people have been looking at is machine learning, and machine learning is fantastic. It's an incredibly powerful technique. It allows you to deal with very high dimensional data. And what I mean by high dimensional data is data with lots of variables. Okay, so typical as a human, if we've got a couple of variables, we can plot them, you know, on an XY graph, and then we can draw boundaries around the different regions of different rock types. And this is what people have done historically. But if you've got 10 variables or 20 variables, there's no way for us to view them. Okay, and this is when we could use machine learning because it has no problem dealing with very high dimensional data. It can have any dimension in space, and it can look for structure in your data. So machine learning, this is why machine learning is very popular. And there's basically two groups that you might apply to, say, drill hole data, and that's unsupervised machine learning and supervised machine learning. So supervised machine learning is when you have a training data set. This means you've taken some representative samples from your drill hole and you've labeled them. You train the classifier and then you give it the new samples that don't have labels. And what it does is it takes the new sample that's unlabeled and it says, which am I most similar to of the things you've already labeled? And it will take that label and apply it to your new sample. So that's supervised machine learning. There's also unsupervised machine learning. In this case, it's just looking for clusters in your data. So, oh, I'm getting some echo. Someone hasn't muted. Thanks. So unsupervised machine learning, you're not giving it any training information. You're just saying find 10 clusters or 20 clusters or 30 clusters of my data, and it will look for structure in your data. So basically, it says that points that are similar belong to the same class. Okay, so if you plot them in feature space, points that are close together are similar, so they belong to the same class. And points that plot a long way away are different, so they belong to a different class. So these two graphs I got here, this data is from the Mineral Systems Drilling Program, which was part of the Deep Exploration Technologies CRC. They drilled a number of holes in the Gawler Craton, and this is the PXRF geochemistry from 6 of those drill holes. And I've just plotted a few of the variables here. The top one's potassium and calcium, the bottom one's niobium and titanium. And I've run a clustering algorithm on this one, the k-means clustering algorithm, and I asked it to find about 30 clusters. And I chose 30 because that was approximately the number of different rock types that the geologist logged. So I wanted to see how it went. And you can see the results there. So the different colors represent the different classes it found. You see it does a pretty good job of grouping things. Okay, so things that are close together are similar colors, same class, and things that are farther away from each other fall into different classes. So if I looked at that, I could say, well, I'm pretty happy with that. That looks like a reasonable division into 30 different compositions. So let's now plot it on the drill hole and see what it looks like. Okay, there's the geologist log. You can see there were only 3 rock types in the geologist log. There was a dacite in purple, basalt in green, and rhyolite in pink. And on the right, that is the plot of the samples down the hole and their classifications. Now you can immediately see that this is a problem. The result is very noisy. And what we mean by very noisy is there's a lot of very small intervals where things have changed. This is very typical of what you see when you apply machine learning. It doesn't matter whether it's supervised or unsupervised. If you have a look at results that people produce from machine learning, you will see that they're typically very noisy like this. And this is a real problem. And why does this happen? It happens because rocks are not homogeneous in composition. So even if you've got a rock that's all basalt, you know that your samples are going to have a little bit of variation, and that's what gives you the scatter on those XY plots. The scatter is the variation in composition of the rock. And if you have a decision boundary that's chosen by the algorithm, so it says, well, I had to divide this region up into 4, and so I put these boundaries in. But if your rock type is very close to that decision boundary, it only takes a very small change in composition, and you change the class that it falls into. And so you typically see these oscillating classes. So if you look at that dacite at the top, on the right-hand plot, it's sort of alternating between pink and teal green. And that's just small variations in composition.
Before you go on holidays, how's it looking? What's the
there's a thing on drill logging to analyze.
Someone's not on mute. Can you mute, please?
I reckon I've got a lot of stuff coming in from drillers.
So how do we overcome this problem? And you might say, well, you chose 30 different rock types. Maybe you just chose too many rock types. Maybe if we had less rock types, we could actually reduce the noise. So let's try that. Okay, so in this example there on the left, the 30 clusters that we originally found, and then I'm going to almost halve the number of clusters to 18, and we get the one on the right. And you can see if you look at that in detail, how some of the groups have merged together to form larger groups in the 18 clusters.
What do you reckon? How's that coming along?
Okay, now let's plot that down whole and compare it. Okay, so again, we got the geology log. Then the first one is the k-means with 18 clusters, and the second one was our original one with 30 clusters. And you can see that we have got rid of some noise, but actually it's still very noisy. And as well as that, we've got a problem, because if you have a look at the purple unit in the 18 clusters, the top one corresponds to dacite, and the bottom one corresponds to rhyolite. So now we can't, not only have we still got a noisy result, but we can't distinguish dacite from rhyolite. So when we've reduced the number of clusters, we've actually reduced the ability for the classifier to distinguish between these two different classes, between dacite and rhyolite. So it's not a very good way to go about reducing the noise. So what is the other possibility? Well, maybe we should just try a different algorithm. Maybe this algorithm isn't very good. So in this case, I've tried a different algorithm. This is the agglomerative clustering algorithm, and we're going to compare the k-means to the agglomerative, both asking to find 18 clusters. And if you have a look at that diagram, the clusters that are very different and really stick out on their own are classified as in a very similar way. They're still grouped in the same classes. But for things where things are close together, the boundaries might be in slightly different places. So let's plot that down whole and have a look. Okay, now we can see the k-means and the agglomerative. And once again, it hasn't really helped us. It's still very noisy, and it still can't distinguish dacite from rhyolite. So it's not the algorithm, it's not the number of clusters. What is the problem we're facing here? and it's about scale. Okay, when you're logging something manually as a geologist, you tend to group things together that are very similar spatially as well as in feature space. So you say, you know, if something's on a borderline, you say, well, what's above it and what's below it? I'm more likely to
That's probably
on its neighbours rather than just looking at it we never look at things in isolation, whereas machine learning algorithms, if they don't take spatial information into account, they just classify each sample in isolation. Okay, and the scale at which we consider our neighbours is the scale at which we log. So you will have heard of loggers referred to as lumpers and splitters. So some people are lumpers, so they're dealing at a very large scale. They're looking at large neighbourhoods and grouping large amounts of similar rock together that is spatially connected, whereas a splitter will tend to want to go to finer scale units. And one of the problems is then if you get a lumper and a splitter logging together that you can't, and now you can't correlate between the two, because you really need a consistent scale. And the question is, what scale should we be logging at? And generally we don't know what scale we want to log at up front. You really feel like you want to log it first and then decide what scale you want. So you almost want the results at a whole range of scales first, and then you can decide which is most appropriate.
He's looking at it. Look, he's looking at it now. No, he's looking at it now.
Is that what he's looking at?
Could everyone please mute their microphones?
there are no spare keys to the Triton.
Sorry, June, I can't find where this person is.
Well, then we need to get a spare set.
They're at my place somewhere. But
There are spares.
go to your emails and just see what's coming from there. Just level.
I saw something had come in. I hadn't.
If anyone out there knows, tell me that would be great. I'm not sure what's. Everyone says they're muted on my.
Well, it depends. It's a billable item on the original thing, and they haven't charged us for it.
Sorry.
I hope they know they're being recorded.
Peter Neville, the manager.
Oh no!
But if you haven't billed us for it, then
I can't see anyone that's not muted.
That was a bit of a surprise to me. I thought it was.
Okay, I think it stopped.
Some sort of meeting.
Okay, sorry guys. Let's carry on. Okay, so if we want to choose a scale at which to log, the analogy I give is like Google Maps. So when you use Google Maps, you zoom in and out. And when you want to see just the large scale features, you zoom right out. And then you can just see the main road systems and the major features. But as you zoom in, not only do things get bigger, but you actually see more detail. So you'll see smaller road systems. And then when you zoom in right into great detail, you'll actually start to see different buildings will start to pop up in different locations, paths. Okay, so we'd like to do something like this in geology. So that we can stand back like we would do on an outcrop. We stand back, we look at the big scale features, and then gradually we zoom in by walking in and having a look, you know, and we pick up a sample and look at a sample, and then you pull out your hand lens and you look at the really small scale features. So when we're doing things manually, we can look at things at all different scales, but with this numerical data, you've only got one scale, and that's the sample scale. Okay, so what would this look like ideally? So here's another geology log, also from the Mineral Systems Drilling Program. This is through Metamorphic Rocks. So you see there's a few more different units. And on the right shows different scales of logging. Okay, this is automated logging. But so you've got this is using the K-means 30 clusters. So on the left hand of those three, you can see when you classify every sample, but ideally we'd like to progressively group it, and so that you're moving to the right and have different scales. Now you could do this by using some algorithm that logged at specific scales, but what if you decided the scale you wanted to log at was somewhere in between those? Okay, so really we want continuous scaling. So this is what we've been working on at CSIRO, and this is what we've come up with. So you can see there you've got the classification of every sample in that log in the middle, and then on to the right of it is the continuous upscaling. So that blocky diagram, we call this the Wavelet Tessellation. On the left-hand side, you can see it's divided into very small units, and then as you move to the right, you can see they're progressively grouped into larger and larger units. And this is what the Wavelet Tessellation algorithm does. the way it works is you start on the right, and you can see that the very first thing that it does at the largest scale is it divides the whole drill hole into 2 units. Okay, so it's a binary algorithm. Okay, then it will take one of those units and then it will split it into 2. And then that one, each of those will be split into 2. So every time you're moving from right to left, you're progressively splitting it by 2 each time. And this is how you end up with your multi-scale. And then you can choose a scale from that, which is appropriate to the problem you're trying to solve. So for example, if you were doing a regional model of this area, you might choose a scale of around 60, for example, about 2/3 of the way along. If you wanted to do a more detailed model, saying that the geologist has logged a skarn there in dark purple, if you go across, that's the orange and dark green and red units. And if you wanted to model the skarn in more detail, you'd go more to the left-hand side of that diagram. So I'm not going to tell you how this method works because there's a lot of maths in it, but I'm just going to step you through the process without involving you in any of the maths required to understand it. So the first thing you do is you look at your variables. So this is 6 variables. They come from, they're actually Y-line logging variables from a public data set. It's a petroleum well on the Northwest Shelf. And you take each variable and you identify the boundaries, potential boundaries in that. And now this method comes from image analysis. So detecting boundaries in images is quite a common problem, and a lot of you will have seen results of boundary detection in images. So this works exactly the same way. And 2 pieces of information come out: the location or the depth of the boundaries. So the black lines are the boundaries and the colored lines are the data. So you can see these black lines are different lengths, and that reflects the strength of the boundary. So the strength of the boundary is dependent on 2 things. It's dependent on the amount of change at that boundary. So if you look at the gamma ray in blue on the left, about 3,000, I think that's millimeters, 3,000 millimeters depth, you've got a very strong boundary, about 2/3 of the way down. And that's because there's a big change there. By contrast, if you look at the neutron density at about 2,400 meters, that's the most right-hand brown signal, you'll see there's a strong boundary in there, and there's not a lot of change at that on the signal at that depth. What that signals, it's wavelength. So that tells you that these are large scale units. Okay, in other words, the apparent thickness is very large. Okay, so it's a balance between the amount of change at the boundary and the size of the unit that you're actually distinguishing. And these are 2 features that geologists would think of when you were doing a lumper or splitter. Okay, it's how different. Do I want to split this out because it's really different, or do I want to split this out because they're really big units and I'm interested in big units? So it integrates those 2 ideas. And you can see the really small features form these really weak little boundaries, and the really strong features form these strong boundaries. And what we do next is we combine all those boundaries from all the variables together, and it gets this combined boundary plot. If, as in many cases, boundaries coincide across the variables, then the strength of the new boundary will incorporate the strength of all the sub-boundaries that contributed to it. So if you get a boundary that reoccurs in many different variables, it will come out very strongly. And it looks something like that diagram on the right there. You can see scale on the x-axis and depth on the y-axis. So you can see the location of all your boundaries and how strong they are. Okay, and then we split it up. We use those boundaries to split it up. So you take the strongest boundary and it splits the drill hole into 2 parts. Then in each part, you take the next strongest boundary. As I said before, it's this binary splitting, and then you end up with these domains. Okay, and then finally, we can color the domains in by classification. So in this case, I've applied 15 clusters from an agglomerative clustering algorithm. This is the first one I'm showing you here is the classification of the sample. So this is where you classify every single sample. So this is the smallest possible scale we can classify things at. It also is very noisy. You can see that there's patterns in there. For example, in the very noisy part down the bottom, you can see that the top part of that really noisy bit is darker blue mostly, and the bottom part is lighter blue. So we'd expect those sort of patterns to come out when we upscale it. Okay, so here are the domains, and they're colored by the classification when we apply it to the domains. And we apply it to the representative value in each domain. And now you can see how as you move from small scale to larger scale, you're sort of grouping those small things together and you're ending up with a much more simplified pattern. So if I wanted to build a regional scale model, I'd probably pick around 80 as my scale. And if I was trying to build a more detailed model, I might pick around 20 as the scale. So now I've got the full range of information that I need to make a decision. So I'll give you an example of selecting scale. So we've actually got a biostratigraphy log for this drill hole, and I've plotted up here, and I've tried to correspond the colors so it makes it a bit easier for the visual comparison. If we wanted to compare how the biostratigraphy compares to the petrophysics, then we select the scale which is most similar, and around about 0.2 to 0.45. Sorry, I realize I've just changed x-axis scale from 0 to 100 to 0 to 1, but anyway, it's the same thing. You can just scale it at any final thing. So if we're looking at this around about 0.2 to 0.5, the scale there is very similar to the biostratigraphy scale. And we can see that at the top of the hole, that the biostratigraphy and the petrophysics change at the same depths. But when we get further down the hole, we can see some differences. For example, if you look at that sort of plummy purple Windalaria unit, about 3,000 millimeters, the petrophysics changes right in the middle of that unit. So even though biostratigraphy-wise it's all the same, the petrophysics isn't the same in that unit. Also, you know, if you have a look down at the Mungaroo Formation shale and the Mungaroo Formation sand, if you look at the splitting that's done by the petrophysics, that boundary isn't quite as clear as what they show in the biostratigraphy. We've got a bit of mixing of the units as you go down. You've probably got a shale and then maybe some interbedded sand and shale before you go down into more of just a plain sand. So this is the sort of way you can use choosing the scale that's appropriate to the problem that you're trying to address. So what are the benefits of using this? Well, it's fast. Compared to doing manual logging, it's very, very fast. Of course, the speed depends on how much data you've got. For example, wireline logging is very dense, so it's going to be slower than if you're doing 1 meter scale geochemistry intervals. But if you've got 1 meter scale geochemistry intervals, you can run hundreds of drill holes in a matter of minutes and get an analysis out. The nice thing is it's very consistent. You know, once you've chosen a scale that you want to work at, you've chosen a classification system, you've chosen your variables, the result you produce is going to always be exactly the same. So if you've got fly in, fly out workforce and one person runs it, someone else comes back, if they know the same parameters they used and they rerun it with some new data, they're going to get absolutely consistent results. It's not going to be different. And this is the nice thing about running things using an algorithm. You save the parameters, you can always repeat the experiment. It's multivariate, which is a big step up from the original method, which was univariate. And so now we can apply machine learning and we can get a classification out of it. So this is a really nice thing. The other thing, and then lastly, it's very easy to change. Because it's fast, you can change the things that you put in. So if you remember from the beginning, I talked about, you know, wanting to run multiple models and you don't have time to build multiple models because you're very pressed for your deadlines. But now you've got a way of changing your variables, changing your classification, and changing your scale if the first one didn't work out. If, for example, the set of variables you chose couldn't distinguish the rock types that you need to be able to distinguish, you can experiment with different variables. Or if your classification wasn't suitable for what you wanted to do, you can simply change your classification and choose a new one. So this idea of being able to run multiple different models is very powerful. Okay, finally, I just want to give you a quick background on how this developed. So geophysicists were using continuous wavelet transform, which is what the mathematical method this is based on. And the continuous wavelet transform produces a picture like these very colorful pictures. On the left, you can see this red to green to blue, and on the right under the word univariate you can see this reddy blue. That's what the continuous wavelet transform looks like. And the problem with the continuous wavelet transform, even though it was this very powerful multiscale method, was that you'd have to be an expert to interpret that plot. It's a mess and it's very difficult to interpret. So people were trying to come up with ideas of ways to make it easier to understand if you weren't a physics or maths person. So originally Cooper and Cowan here developed the blocking method. So you can see out to the right of the continuous wavelet transform, they've extracted information at a scale of 5 and a scale of 8. So the black line that goes through the middle of the continuous wavelet transform, that's the scale of 8. So by extracting at different scales, they could get different information. But you can see it would be very hard to decide what scale to select at. So this is why we developed this wavelet tessellation, and it's based on some work by a guy called Witkin, who was also in image analysis and was trying to figure out how to segment images. So it's based on his idea, and now it's like a continuous, it's almost like a continuous blocking, okay, all the way from the smallest scale to the largest scale. So this was developed as part of the Deep Exploration Technologies CRC where I worked, and it was eventually commercialized by Imdex. It's in their IAGAS, so if you use IAGAS, you'll find the wavelet tessellation in IAGAS there. And it's very nice because it's all integrated with how IAGAS works, and you can do your analysis and then integrate it with all the other analysis you do in IAGAS. The only thing to note is the one in IAGAS is univariate, and that's all we had time to develop during the DTCRC. Subsequent to that, CSIRO has been doing more work on this, and now that's where we've developed the multivariate. We've also made the algorithm a bit more efficient, faster, and we've made our multivariate version available on the web. So we've got a web app, it's called Data Mosaic. And if you're interested in having a try, at the moment it's free to try for anyone. Basically, it steps you through a series of pages. It's a very simple workflow. You upload your data, you find the boundaries, you create your mosaic or your tessellation, and you come up with a classification and apply that to the tessellation. So you can pretty much see those steps there. It's very simple, and at the end of it, you can save the images if you're after the images, or if you want to apply it to your whole data set and save it as single scale pseudo logs, you can do that and then import it straight into your modeling software. So, so that's pretty much all I'm going to talk about today on the methods, and now we can move on to looking at the case studies. So I'm going to hand over to Margot now to do that.
Yeah, thank you, June. Can you hear me?
Yes.
Okay, I had the wrong screen. Okay. Sorry, I'm just going to share the right screen. Give me 2 seconds. Okay, it's not doing what I want it to do. It's not showing anything. I'm sorry, technical issues here. Just 2 seconds. Oh, there. Sharing emitting, yes. All right, getting there. Just want to view again, I'm sure. All right, getting there. Thanks, June, for the technical side of things. So I started working with June on her first version of the tessellation, the wavelet transform, a little while back, and that was when it was still a univariate method. And we decided to apply it to try and better understand and model a nickel copper PG ore body, which is the Kibbutz mine in northern Finland. So I'm just going to quite briefly step you through what we did and the genetic implications, and then Jess will move on to multivariate uses. So the Kibbutz Intrusion is a large mafic, ultramafic layered intrusion that's in northern Finland, and it contains about low-grade disseminated sulfides, about 230 million tons resource, and it's got cryptic igneous layering within it, which is quite hard to recognize using just geochemistry. So this is what the actual 3D model of the Kibbutz looked like. So in gray here you have the outline of the intrusion. Trying to see if my pointer works. Yep. Okay. So this is the outline, and they didn't have much model inside it because it's really hard to actually model igneous layering due to just the cryptic layering. And this is the only little geological model they had within the intrusion. And then they also had, well, the exploration team had some sort of a model of the ore body, which was quite wrong and and not really practical. So, but they also had access to a gigantic assay database of over 92,000 analyses, and a lot of them had the full suite PGEs, which is quite incredible. The GTK did a lot of work at that time. And so we decided to try and use that data set and combine our internal expertise on magnetic nickel copper PGE systems. So Steve Barnes and I worked on that, and combine it with June's expertise and recently developed a data domaining tool. And the aim was to get an automated and objective 3D classification of the ore types within the Kibbutz Intrusion. And that database represented a huge wealth of information, but it was really hard to know how to integrate it and how to distinguish significant trends and patterns from actual background and short-range variability. And so the multiscale domaining tool was perfect for that. So we use our internal knowledge of magnetic nickel copper PGE systems to try and define different ore types. And we defined 4 different main ore types. One of them was what we call like no ore. It's like a very where the sulfur was below 0.5%. So we got rid of all of that data. And then we had the false ore, which was high sulfur but very low nickel, less than 2%, which is in blue here. So this part of the diagram. So this is palladium tenor, versus nickel tenor. So that's the amount of nickel and the amount of palladium that you have within the sulfides within the ore body. Then we have the second ore type, which had moderate nickel and quite high palladium values. And then the same here that had moderate nickel but low palladium values. And then you had that final ore type, which is the most interesting one within the ore body, which is the high nickel, high PG ore here in red. So those are the 4 different ore types that we decided to use. That was our classification. Now, what we did is actually apply the wavelet tessellation and the multiscale domaining that June's been talking about to 3 different variables. Sulfur, that's what I'm showing here. So that's just sulfur downhole. That's one example of one of the drill hole that we had. That's just sulfur in percent. And so we used sulfur, nickel tenor, and palladium tenor. So we did for each of these variables, we ran through the tessellation, the continuous transport, and the tessellation, and then filtered it to clean it up a little bit. And then we chose one scale in particular that we were interested in. And that's because we only were using the univariate data mosaic. And so we had to do it on all the different variables, pick a scale, and then combine those. Nowadays, with multivariate, we could actually do that all together, and I'll show what that would look like in a minute. So this is the results for all 3 variables. So this is sulfur here, nickel tenor, and palladium tenor. So one of the drill hole. So each of those variables went through the process, and then we combined the boundaries. Once we had these different domains, we applied the classification we had designed, and we got a log of the different ore types downhole. So now that we have multivariate, we could get that result here, but you could get it with actually at different scales. And you could decide on the scale after you've combined your 3 different variables, which is a lot more powerful. So this is just a screenshot from just putting the same data set through data mosaic. And this is what you would get basically. So those are 3 variables, sulfur, nickel tenor, and palladium tenor. Combine the boundaries, and then you get your multiscale automated domain downhole. And then you can actually pick the scale that you want to work at after having already combined your different variables. But we didn't have that at the time, so we did it just this way, the way I showed you. So this is the results we obtained for every single drill hole. And so this is the result in 3D. So this is the outline here. So the intrusion goes a bit deeper, a bit further down here, basically the outline of the intrusion. That's just the drilling that was done to actually differentiate the different ore types. There was a lot of data. And so this is when we applied the classification for each assay. So each meter point, basically, we gave it the same classification for the different 4 ore types. And this is extremely noisy, which is why we wanted to use the tessellation. And this is after the automated domaining at a specific scale that we'd chosen. And you can see how you can really see the trends a lot better. You get rid of the noise, but you still have important feature, like when there's a lot of difference in the actual composition and you get a different ore type, even if it's a small interval, you still see it. So you don't lose that in the process. So this is just a close-up here. So this is before the automated domaining, and this is after. And so just a little bit on the interpretation, the geological interpretation of that. So this is just a little model now of how the ore types were distributed within the intrusion. And what we realized is that you had a shallow inward dipping of the layering of the sulfide composition, and you had an increase of the tenors from outside of the intrusion towards up towards the top of the intrusion and the center of the intrusion. So you can see you go from false ore, which is basically just sulfur that's probably been assimilated from the contrary rocks, and you create a bit of sulfides, and then you increase the tenors in nickel and palladium as you go up to these really high PG, high nickel ores. And so you get that metal enrichment of the sulfides, and we think that's due to the result of interaction of your sulfide droplets with the silicate melt as the system increases its size. So this is just a little model of what we think it looked like. So it started as a layered complex like this, and then as the increase of magma flux arrived, you had more interaction between the silicate melt and your sulfide blebs. You enriched your ore, and you slowly built your intrusion into what it is now with the ore types. So that's a really, really quick interpretation. If you are interested in exactly how that worked, we did publish this a little while back. So this is just a paper here in Ore Geology Reviews. But basically, that's where we really saw the power, how powerful this technique was into getting a really consistent and objective reduction of the number of units in each drill hole, and allowed us to really build a simplified 3D model of the ore body. And that gave us insights on the genetic processes that were at play at Qubits. You get really consistent results over a massive database, and it's a really time-saving method. And also you don't lose, as I was saying earlier, the high nickel, high PG ore, which is small intervals quite often, but was quite different in its composition. We didn't lose that information by using this technique. So I think that's all I was going to say, and I might leave it to Jess to take over. Hopefully that will be smooth. Fingers crossed. There we go. Thanks, Margot. Perfect. Cool. Are you muted? Yep. We good now? Okay. That was unusual. All right. So today I'm going to walk you through a case study where we use the multivariate method. So I've titled my talk Lumpers, Splitters, and Navigating the Fortescue Group Stratigraphy. So this is a project I worked on with my colleagues Mark Pierce and Sam Spinks, looking at some new diamond drilling from the Fortescue Group that was done through the GSW EIS program with Artemis Resources. So just a bit of geological context. So we were looking at the Fortescue Group a couple hundred kilometers south of Karatha, in an area where just recently has become kind of famous for conglomerate hosted gold showings. So the new gold rush, people were finding gold in the rubble everywhere. And there's some old drilling from the 80s at the drill hole DD84MF1, which had some gold nuggets at the base of one of the conglomerate units. And so some new drilling was undertaken to try and understand the lateral extension of those units, and kind of the regional basin architecture, and also look at the Fortescue Group stratigraphy. So this provided an opportunity to really understand the Fortescue Group in an area where it's not very well studied because it's undercover, and look at the sediment provenance and mineral prospectivity across the area. So these are the drill hole I'm going to present to you is 1880 AB01. So this presented some challenges. Firstly, we had about 2.5 kilometers of drill core, which was logged by several people. So there's logging inconsistencies, multiple geos, lumpers versus splitters. So it's really difficult to correlate the stratigraphy across the area between these two holes on anything other than just the group formation level. So the drill hole I'm showing you is collared in the Tumbiana formation, which is a metasedimentary unit which overlies the Kailina, which is a volcanics, and then the Hardy formation, and then the basement. And so we'll be working with this kind of section of the
the drill core right there. So that's the first difficulty. The second is, how do you go about sampling over 2,000 meters of drill core for really kind of high resolution analysis? So we wanted to do whole rock geochemistry, isotopes, boutique isotopes like chromium and strontium, and also do some Maya mapping. So that presents a problem in itself. So I'm going to go through a couple of these challenges. So firstly, the long prism splitters, and then the misclassifications that occur. So this is the, believe it or not, the simplified geologist log right here of the first hole. And you can see if you zoom into this one section in both holes, it's clearly been logged by two people, a splitter and a lumper. So how do you begin to correlate those kind of sedimentary units? And then there's also misclassification. There's a 100-meter section logged as an amphibole porphyry, which is a new type of rock to my knowledge. So there's things that could be addressed by looking at this an objective way and incorporating geochemistry. So the geochemical data that we used is continuous downhole XRF. So this was collected using the mineralized system, which collects kind of centimeter resolution XRF data, which can then be binned to 10 centimeters or 1 meter. We binned it to 1 meter to improve the counting statistics, and then what you get there is just a continuous log of your geochemistry. So the first thing we did was we used the univariate method, which Margot's already talked about in detail, and so is June. And this is pretty good. I mean, you correlate the major stratigraphic units across kind of 5 kilometers between these two holes. We used chromium, zirconium, and titanium, which are pretty standard elements for distinguishing between different igneous units. We were able to correlate the volcanic flows, this particular marker horizon. So here you can see just the raw XRF results downhole. This is the first hole, and this is the second hole, which is 5 kilometers to the southwest. You can see you can actually correlate the stratigraphy quite well. But there's limitations. There's really no descriptors on this. You don't really get lithology discrimination. You can say, oh, this has more chromium, zirconium, but nothing about alteration or what type of rock it is or provenance, that sort of thing. So for that, you kind of need to go to multivariate methods. The other thing we're able to use the univariate method for is looking at domain variability. So as you export your univariate results, you also get an indication of boundary domain mean and domain variability. So this tells you how much variability you have within a given unit, and that can be useful for understanding sampling strategy. So if you have several units which are super homogeneous, you probably can sample systematically every 10 meters without any problem. But if you have some units which are super heterogeneous, you may want to sample on a tighter spacing. So that was helpful in terms of selecting samples for high resolution analysis like isotopes and trace elements, for instance. So, but what we really needed was to look at the multivariate method to really understand, because we're working with rocks that range from kind of granitic to mafic to almost ultramafic. And so using just 1 or 2 variables is not enough to discriminate between them in a really effective way. So for that, the first problem you come into is you need to decide which elements to use. And this is where the geologist comes in. There is no, one fix-all machine fix for doing all this sort of work. You need to use your domain knowledge. So the first thing is consider your data and the limitations of your data. Are you working with XRF data or assay data? Are some elements dodgy? So maybe you don't want to use magnesium or light elements from your XRF data. Do you have detection limit issues? It's not super helpful if you're trying to, look at rock types to use an element like copper that is below detection limit in half your rocks, for instance. Are there overlaps in your geochemical data? Have a really clear question about what you're asking and select meaningful input variables. So are you trying to classify different rock types or different ore types? You're going to use very different elements for those. And then reduce dimensionality and don't incorporate spurious information. So if you know that 2 elements correlate with one another, could reconsider whether you should put those both into your data set, because that can create artificially strong boundaries. So for instance, one you might want to be careful with is potassium and rubidium in some cases. So in our case study, we use a subset of elements. We use chromium, zirconium, titanium, and then strontium, rubidium, potassium, and silica, because these are pretty standard elements for distinguishing both mafic and more kind of granitic composition rocks. And we use an additive log ratio method over titanium to work with this data. So the first thing, like June mentioned, is you do the sample classification. So we created a lithogeochemical log. We used k-means clustering for this, which has some limitations, but because it assumes that all your clusters have the same number of samples. But it's a pretty standard method, and this being kind of a case study that's to show, it was published as a case study, open access to kind of show how this works. It's a useful benchmark method. We also selected 20 clusters, and that's because there's 20 geologically logged units. And so just to keep that consistent comparability, you can see it splits up pretty well, the units. But what you end up with is, like June mentioned, a log that has many, many small units. When you compare that to the geologist log, you see that, well, the geologist log is subjective and it's not diagnostic. You've got this information on texture and things like that. You also have 1 million units. The lithogeochemical log also has 1 million units, but it's a little bit more objective, and you've got some diagnostic things. So we've assigned labels to these different units based on our understanding of whether it's a sedimentary rock or basalt, and something to do with the geochemistry just for this. But you see, when you put them together, they're complementary. They both become more meaningful if you put together kind of the textural information with some of the geochemical information. So you begin, even before you begin your domaining, you can add some value to your geologist log by doing something as simple as a clustering classification exercise. And from there, what we do is a boundary detection. So these are the elements we use, again, with the ALR over titanium. And you'll notice that the boundary strength, again, is a measure of scale. So these are the boundary strengths of a given element. You might notice we did use both potassium and rubidium in our example, but you can see that they show different boundaries in different locations. And so while you may be, for instance, artificially enhancing this particular boundary, if you leave one of them out, you are missing some boundaries. So we felt it was important to keep them all. And then when you put that together with the data mosaic to do the multivariate boundary detection with the classification, what you end up with is this multi-scale kind of boundary. So where your largest areas here kind of inherit their classification composition based on the smallest units. So what you get is a plot that preserves information on mixed rock types in different domains, and provides your multi-element geochemistry in a way that's reasonably easy for you to kind of digest. And the other good thing you can do is, because you have this multivariate capability, you can use that to enhance your sampling strategy as well, because you have an understanding of your domain variability based on an objective kind of geologically relevant rock type or cluster. You can understand whether your variability is from many small units of very different compositions or just 3 different units. And then from that, you can extract logs at different scales. So the scale at which you extract your log is entirely question dependent. If you're trying to understand just the boundaries between the main rock types, go ahead, extract at a large scale, something like this 0.25 scale. If you want to distinguish different volcanic flows through the central area and maybe alteration, flow tops and stuff like that, you might want to extract it at a finer scale. And so not only can you export these pseudo logs, what I think is probably the most interesting bit is you can export a hierarchical log in a kind of CSV format, which very closely models what a geologist would do, where you can, in this particular example, we've exported 3 different lithologies, so lith 1, lith 2, and lith 3 at the scale of 0.25, I believe here. And I've just shown for comparison, here's the geolog, which is super complicated, but you can look at this pseudo log, which is easier to digest, but still retain the information that's in that geolog because you have all of this in your hierarchical logging. And you can see, even compared to the univariate method, where you just have an understanding of kind of what's the change in one rock type, you're getting more information preserved using the hierarchical log from the multivariate method. And so just some final thoughts for applying this is, when you are looking to do something like this, make sure you have a clearly geological question in mind and scale accordingly. That's kind of the key thing. And make sure you use your domain knowledge in developing your method for doing it. Know your data, choose your variables wisely, and know the limitations of your data. And ultimately, if you do that, what you'll end up with is objective, consistent, geologically relevant logs, which you can quickly output, which are really complementary to traditional logging because it presents a lot of multi-element geochemistry in a way that's easy to digest visually. And not only that, you can export the hierarchical logs, and you can also export the pseudo logs and as interval data and use that in 3D visualization software. So here's just, again, an example of the different scales. And I know someone asked earlier about alteration as well. And in this case, because we used the multivariate, where we didn't just have lithological discriminators, we had things like potassium and stuff. We actually were able to distinguish volcanic flows or sections of flows which were hydrothermally altered from other ones if you go to a higher scale. So this kind of top area here is a really altered area where these are all smaller flows which are potassically altered. And so when you look at the clustering, you can actually see they all cluster with higher potassium values. So it's great for distinguishing both alteration and lithogeochemistry, or so primary lithologies, depending, again, what variables you put in and what scale you want to look at. And so if you want some more information about the math behind this, it's in a paper that just came out in Mathematical Geoscience, which is open access and available online. And June would be happy to answer questions about that, I'm sure. So I'll leave it at that.
Just quickly before we finish, we're close to 2 p.m., but I'd like to point out the fact that we are organizing an online workshop on the 13th and 14th of July. So it's in two 3-hour sessions. And there's a link here for the registration, which is on Eventbrite. And we'll put that up also on LinkedIn and Twitter and everything after this presentation. And if you have any questions, you can send an email to the email that's down there on the right, datamosaic@csiro.au, and one of us will answer.